At this point, I'm going to add in a discussion about what I'm going to call the equivalency theorem. And the equivalency theorem is going to be a theorem that we're going to talk about all semester, and we're going to add bit by bit as we go along. But we're already far enough to be able to see lots of equivalences that we can talk about. So the equivalency theorem says that the following are equivalent. So the following are equivalent for an n by n matrix A. So for an n by n matrix A. And so the first thing is that the determinant of A will be non-zero. And it turns out that if the determinant of A is non-zero, then we get all of the following consequences. We get that A has an inverse. Okay, so that's a big one right away. So if the determinant of A is non-zero, then A has an inverse. We also know that the system AX equals B has a unique solution. So we've seen this as well, that if A has an inverse, then AX equals B has a unique solution. And that unique solution is, I should just add, is X equals A inverse times B. And if A inverse exists, you can just compute that. You have exactly one solution and you're done. This is a related idea, but if you have AX equals 0, so instead of having B, remember, is the right side of the equation whenever you have your system. So it's, in other words, all the constants that you get in your system. If all those constants are 0, you again have a solution, and it's called the trivial solution. So this is only the trivial solution, and that's namely X equals 0. And really, these two are saying the same thing if you think about it, because if A has an inverse, then X is going to be A inverse times 0, and that's 0. So remember, multiplying by the 0 matrix really produces 0. So those are really saying the same thing. A few other things to say. One is that A, and I want to just think very carefully about how to word this, but if the determinant of A is non-zero, then A has, so the reduced row echelon form of A, and I wrote that backwards, that's silly. Let me just write it the way I want to write it, and then you don't have to equivocate. And the reduced row echelon form of A is the n by n identity. So remember when we were trying to find the identity at the start, and what we did is we took the matrix A and we augmented it with the identity, and then we tried to get the identity on the other side. When we did that, the way that we could do that is if the matrix A can be row reduced to the identity. And if that's the case, then you can find an inverse, and therefore the determinant's non-zero, and that's what that says. And then the final thing, and this is, again, equivalent to saying that the row reduced echelon form of A is the identity matrix. That's going to happen if and only if A can be written as a product of elementary matrices. So if A is a product of elementary matrices. And that should be pretty straightforward that those two are equivalent, because if A can be row reduced to the identity, then all these row operations are equivalent to multiplying by an elementary matrix. And therefore, if you can row reduce all the way down to the identity, you can write A as a product of all these elementary matrices. Okay. Now, this equivalency goes the other way as well. When I say that these are equivalent, what I mean is that there's only two options. Either all of these statements are true, so either all 6 of these are true, or all of these statements are false. There is no in between. They're either all true or they're all false. That's it. That's all that can happen. Okay, so when I say that they're equivalent, that's what I mean, is that either they're all true or they're all false. They all have the same truth value. And so if the determinant of A is non-zero, from that you can conclude that A has an inverse, AX equals B has a unique solution, AX equals 0 has, again, a unique solution, in this case the trivial solution. A can be row reduced to the identity matrix. A can be written as a product of elementary matrices. That's all equivalent to saying that the determinant of A is non-zero. Moreover, if the determinant of A is 0, then A does not have an inverse. So if the determinant of A is 0, A does not have an inverse, AX equals B does not have a unique solution. It'll have either 0 or infinitely many solutions. AX equals 0 does not have a unique solution, therefore it has to have infinitely many, because we have at least one. X equals 0 is always a solution to this system. And so if there's not a unique solution, there must be infinitely many. A cannot be row reduced to the identity matrix, and A is not the product of elementary matrices. That's all equivalent to saying that the determinant of A is equal to 0. Okay, so this is called the equivalency theorem. We're going to add to this theorem as we go along over the course of the semester.